Imagine you're standing in front of a solid concrete wall. You run at it full speed, and instead of bouncing back, you walk straight through it like it's made of mist. Impossible, right? In our everyday world, yes. But in the quantum world, particles do exactly that every single second. This is quantum tunneling, the mind-bending process that lets particles pass through energy barriers they classically have zero right to cross. It powers the sun, makes nuclear decay possible, lets us image atoms one by one, and might one day unlock quantum computers that break today's encryption. Today on Physics Vault, we're spending the full hour going from zero to expert on how and why quantum tunneling happens. Stick around. By the end, you'll understand the math, see real experiments, and realize the universe is far stranger than it looks. Let's tunnel in. Let's start with what we expect from everyday experience. In classical mechanics, if a particle doesn't have enough energy to climb over a barrier, it simply bounces back. Think of a ball rolling toward a hill. If its kinetic energy E is less than the potential energy V at the top, it rolls back down. No exceptions. This is why you can't walk through walls or why a car can't drive through a mountain. Energy conservation is absolute, but the quantum world doesn't care about our intuition. Everything changes when we realize particles aren't just tiny billiard balls, they are also waves. Louis de Broglie proposed in 1924 that every particle has a wavelength L, E, or H. Electrons, protons, even baseballs technically have wave nature, but the effect is only noticeable for tiny masses. When a wave meets a barrier, it doesn't stop completely. Part of it reflects, part of it transmits, and part leaks into the forbidden region. That leaking is tunneling. The star of the show is the wave function. Next, it doesn't tell us where the particle is, it tells us the probability of finding it. X2 is the probability density. The time-independent Schrödinger equation governs it. Chacha frac, which abortan 2-man frac, d2 npsi, dx2 plus vx apsi, u npsi, inside the barrier where EV, the solution is no longer oscillatory. It becomes exponentially decaying. Higher psi x where propto, e port kappa, is e quad, a text where on quad, a kappa, harker skier, and frac, po v0, e, robarus. That exponential tail means there's a tiny but real chance the particle is found on the other side. For a rectangular barrier of width L and height V0, the exact transmission probability is complicated, but when the barrier is thick, KL1, it simplifies to T japrox 16 off rack and V the left 1 E frac E V0 right E the tur kappa L as the exponential term dominates. Even a small increase in barrier width or height makes tunneling exponentially less likely. That's why macroscopic objects never tunnel through walls. Their mass makes key enormous. Inside the nucleus, alpha particles are trapped by a huge Coulomb barrier. Classically, they're stuck forever, yet they tunnel out, and that's why uranium decays with a half-life of billions of years. Protons in the sun don't have enough energy to overcome the Coulomb barrier, except when they tunnel. Without tunneling, the sun would go out instantly. Electrons tunnel through thin insulating layers in your phone's NAND flash. That's why it remembers data without power. Hawking radiation, black holes evaporate via tunneling, quantum computing, tunneling in qubits, future tunnel field effect transistors that could end Moore's law slow down. Philosophical, the universe is probabilistic at its core. Quantum tunneling is not a rare curiosity. It's the reason stars shine, atoms decay, and your phone works. It shows that reality at the smallest scales runs on probability, not certainty. Next time you look at a wall, remember, at the quantum level, that wall is leaking tiny waves of possibility every instant. If you enjoyed this deep dive, smash that like button, subscribe for more hour-long physics deep dives, and comment, what quantum phenomenon should we cover next? Thanks for tunneling through an hour with me. I'll see you in the next video.